NASA's Pioneer 10 and Pioneer 11 spacecraft once puzzled scientists with an unexpected small acceleration toward the Sun when they reached about 20 astronomical units from Earth. This effect, known as the Pioneer Anomaly, sparked years of debate about whether unknown forces or new physics were involved. Decades later, careful analysis revealed a more practical explanation rooted in spacecraft engineering. In this video, we will look at what was observed, why it mattered, and how the mystery was solved. Let's get started. NASA launched Pioneer 10 in 1972 and Pioneer 11 in 1973 during the early era of deep space exploration. These spacecrafts were designed to explore the outer planets and then continue outward beyond the known boundaries of the solar system. Pioneer 10 became the first spacecraft to fly past Jupiter, and Pioneer 11 later flew past both Jupiter and Saturn. After their planetary encounters, both probes were placed on long trajectories, carrying them steadily away from the Sun toward interstellar space. As part of normal mission operations, scientists tracked the probes using radio signals exchanged between Earth and the spacecraft. By measuring tiny changes in the frequency of these signals, known as Doppler tracking, engineers could calculate the spacecraft's velocity and acceleration with extremely high precision. This method is sensitive enough to detect even very small deviations from predicted motion. It was through this long-term tracking that something unusual appeared. When both Pioneer 10 and Pioneer 11 reached distances of about 20 astronomical units from the Sun, their motion began to diverge slightly from predictions. The spacecraft were still moving outward, but they appeared to be slowing down just a bit more than expected, as if a small force was acting on them in the direction of the Sun. The effect was extremely subtle, but it was consistent and persistent. It appeared in data from both spacecraft and remained visible over long periods of observation. When scientists compared the observed motion to their navigation models, they found a small but steady discrepancy. Mathematically, the discrepancy could be removed by adding a constant acceleration term pointing toward the Sun. This became known as the Pioneer Anomaly. What made the situation scientifically significant was not the size of the effect, but its consistency. Two different spacecraft, launched a year apart, following different paths, showed the same unexplained behavior at roughly the same distance from the Sun. This made it difficult to dismiss as random noise, data error, or isolated system failure. At first, scientists approached the anomaly cautiously. Deep space navigation involves many small forces, and long-duration missions can accumulate modeling uncertainties. But repeated analyses showed that the effect remained even after known forces were included in calculations, including gravitational influences, solar radiation pressure, and standard spacecraft system effects. This raised a serious scientific question. Was there an unknown physical influence acting on the probes, or was something missing from the models used to describe their motion? The Pioneer Anomaly attracted attention because precision spacecraft tracking is one of the most sensitive ways to test physics in space. At large distances from the Sun, fewer forces act on spacecraft, making their motion simpler to model and deviations easier to detect. This makes deep space probes valuable tools for studying both engineering systems and fundamental physics. Because of this, the anomaly was treated as a real scientific problem, not a curiosity. Early discussions explored whether the effect could point to new physics. Since the acceleration appeared constant and sunward, some researchers considered whether it could reflect a deviation from Newton's inverse square law of gravity at large distances. Others explored whether it might be linked to general relativity, cosmic expansion, or large-scale cosmological effects. A wide range of theoretical ideas appeared in scientific literature, including modified gravity models, cosmological time effects, and exotic spacetime interpretations. These proposals were not sensationalism. They were legitimate attempts to explain unexplained data using theoretical frameworks. At the same time, more conservative explanations were also pursued. Engineers and physicists began re-examining the spacecraft themselves in detail. One key focus became thermal physics. The Pioneer probes were powered by radioisotope thermoelectric generators, which produce electricity by converting heat from radioactive decay. This means the spacecraft continuously emitted heat into space. Onboard electronics also generated heat. From basic physics, radiation carries momentum. If heat is radiated evenly in all directions, the net force is zero. But if heat is emitted unevenly, it creates a small recoil force, similar to a very weak, continuous thrust. Initially, this explanation was difficult to evaluate because detailed thermal models of the spacecraft were incomplete, and early telemetry data was limited. The heat distribution, surface properties, and internal structure of the probes were not fully represented in early navigation models. Years later, scientists recovered detailed engineering data and reconstructed full thermal models of the Pioneer spacecraft. By simulating how heat was generated, conducted through the structure, reflected by surfaces, and radiated into space, they were able to calculate the resulting recoil force. The results showed that anisotropic heat emission from the power systems and electronics produced a small, steady force in the sunward direction. The magnitude and direction of this force matched the Pioneer anomaly precisely. Once this thermal recoil force was included in the navigation models, the anomalous acceleration disappeared. The discrepancy was not due to new physics. It was due to a small engineering effect that had not been fully accounted for in earlier analyses. The anomaly was real in the data, but its cause was conventional physics. The resolution of the Pioneer anomaly carries important implications for both space science and scientific methodology. First, it demonstrates how extremely small forces can have measurable effects over long timescales in deep space. In environments where few external forces act, even weak effects like thermal radiation can accumulate into detectable changes in motion. Second, it highlights the importance of detailed spacecraft modeling. Modern missions now incorporate far more sophisticated thermal, structural, and systems modeling precisely because of lessons learned from cases like Pioneer. Engineers now design spacecraft with a better understanding of how heat, radiation, and internal systems can affect long-term trajectories. Third, the Pioneer anomaly provides a clear example of how science responds to unexplained data. The anomaly was not ignored. It was investigated seriously, debated openly, and analyzed over many years. Multiple hypotheses were explored, from exotic physics to engineering explanations. The final solution did not come from speculation, but from better data, improved modeling, and deeper analysis of the spacecraft systems themselves. This case illustrates a core principle of scientific practice. Anomalies should be investigated rigorously, but not prematurely interpreted as revolutionary discoveries. The article also references another phenomenon known as the flyby anomaly, where some spacecraft have gained slightly more speed than predicted during Earth gravity assist maneuvers. Unlike the Pioneer anomaly, this effect is not consistently observed across all missions and remains less well understood. However, historical patterns in space science suggest that such anomalies often receive conventional explanations as measurement techniques improve and models become more precise. The Pioneer anomaly is now considered a resolved scientific case. It no longer represents a challenge to gravitational theory or cosmology, but it remains important as a lesson in precision science and long-duration spaceflight analysis. Future deep space missions will continue to push the limits of navigation accuracy. As spacecraft travel farther and operate longer, similar discrepancies may appear. The Pioneer case provides a blueprint for how to approach them: careful measurement, conservative modeling, and long-term analysis. The story of Pioneer 10 and Pioneer 11 is not about discovering new forces in the universe. It is about how scientific understanding improves through patience, evidence, and refinement of models. The Pioneer anomaly was real. Its cause was simple physics, not new laws of nature, and it changed how deep space missions are designed and understood.